In November 2018, a team of NASA scientists gathered around data streaming in from a spacecraft launched 41 years earlier, and what they saw made several of them go completely quiet. Not the excited quiet of a team waiting for confirmation. The stunned quiet of people realizing that everything they had modeled, everything they had predicted, everything they had argued about in academic papers for 30 years was only partially right. Voyager 2 had just crossed the edge of the solar system. And unlike its twin, it had done something that had never been done before in the history of space exploration. Something that, scientifically speaking, should not have been possible at all. The twin probes. A quick catch-up for those who skipped physics class. Let us start at the beginning, because some of you are going to need a little context before we get to the part where NASA engineers perform surgery on a spacecraft 11 billion miles away. And yes, that sentence is real, and we will get there. When the summer of 1977, NASA launched two spacecraft 16 days apart. Voyager 1 went up on September 5th. Voyager 2, confusingly, launched first on August 20th. Nobody seems to want to talk about that particular naming decision. The people in charge of labeling things at NASA were clearly having a rough week. Both probes were built for the same original mission. Take advantage of a rare planetary alignment, one that only occurs once every 175 years, and use the gravity of the outer planets to slingshot across the solar system. The mission was called the Grand Tour. It was, and remains, one of the most audacious things human beings have ever attempted. Voyager 1 swung past Jupiter and Saturn, and then used Saturn's gravity to arc upward out of the plane of the solar system, heading north and fast. Voyager 2 took the scenic route. It visited Jupiter, then Saturn, then became the only spacecraft in history to fly past Uranus and Neptune. Think about that for a moment. We have visited Neptune exactly once. One time, with one probe, launched in 1977. We have not been back. If that does not make you feel some kind of way, I genuinely do not know what to tell you. After Neptune, both probes kept going. Not because anyone was steering them. There was nowhere to steer them to. They simply kept moving in the direction physics told them to move, carried by the momentum of planetary gravity assists, drifting outward into the dark at roughly 35,000 miles per hour. Most people assumed they would fade into irrelevance. Old hardware, old software, running on less computing power than the watch on your wrist. Scientists kept listening, but the wider world largely forgot about them. That was a mistake, because decades later, Voyager 2 was about to do something that its more famous sibling never could. The boundary that shouldn't exist. Before we can explain what Voyager 2 did, we need to talk about something called the heliopause. And I promise this is not going to be a physics lecture. Well, it is going to be a little bit of a physics lecture, but a dramatic one. The sun does not just sit there producing light and heat. It constantly exhales. A stream of charged particles, electrons and protons moving at hundreds of miles per second, flows outward from the sun in all directions. This is called the solar wind. It fills the entire solar system, pushing outward in a vast invisible bubble. That bubble is called the heliosphere. Everything inside it, every planet, every asteroid, every comet, every spacecraft we have ever launched, is technically inside the sun's atmosphere. We do not live on Earth so much as we live inside the sun, but the solar wind cannot expand forever. Eventually, far beyond Neptune, it slams into the interstellar medium. That is the technical name for what fills the space between star systems. Thin, cold gas and dust. The ancient remnants of dead stars, drifting in the spaces between everything. Where the solar wind meets the interstellar medium and loses the battle. Where the pressure from outside finally overwhelms the pressure from inside. That is the heliopause. It is the actual edge of our solar system. Not a line we drew on a map. a real physical boundary where the sun's influence ends and true interstellar space begins. For decades, scientists debated where exactly this boundary sat. They built models. They argued at conferences. They published papers with equations long enough to wallpaper a small house. The estimates ranged from roughly 80 to 100 astronomical units from the sun. 1 astronomical unit is the distance from the Earth to the sun. So we were talking about 80 to 100 times the Earth-Sun distance. Remote does not begin to cover it. And here is what made the heliopause so scientifically tantalizing. Nobody knew exactly what it looked like up close. Was it a sharp boundary? A gradual transition? A turbulent churning zone? The models disagreed. The arguments continued. And then Voyager 1 arrived. Voyager 1 got there first. So why isn't this about Voyager 1? In August 2013, NASA confirmed that Voyager 1 had crossed the heliopause, becoming the first human-made object to enter interstellar space. It was a genuinely historic moment. Front-page news. Scientists who had spent their careers working on Voyager openly wept in press conferences. The probe had been traveling for 36 years, and it had finally left home. The data Voyager 1 sent back was extraordinary. It confirmed the existence of the heliopause as a real boundary. It measured the change in magnetic field direction. It detected the sudden increase in galactic cosmic rays, the high-energy particles from outside the solar system that the heliosphere partially shields us from. It measured the drop in solar wind particles. Voyager 1 proved that interstellar space was real and reachable and measurable. That is not a small thing. But here is the problem. And it is a problem that haunted heliospheric scientists for years after 2013. Voyager 1 could not measure plasma. The plasma science instrument on Voyager 1 had failed back in 1980. It stopped working before the probe even reached Jupiter's orbit. Scientists could infer plasma conditions from other measurements, from changes in the magnetic field, from cosmic ray data, from the behavior of electrons. But they could not directly measure it. They were reading the shadows on the wall and trying to describe what was casting them. Plasma measurement at the heliopause was not a minor detail. It was the central question. The solar wind is plasma. The interstellar medium contains plasma. The interaction between them at the boundary is a plasma phenomenon. To understand what the heliopause actually is, you needed plasma data. Direct, measured, unambiguous plasma data. Voyager 1 crossed the most important boundary in our solar system with its plasma instrument broken. It was like sending a food critic to the greatest restaurant in the world and finding out they lost their sense of taste 3 years ago. They can still tell you things. Useful things even. But you are missing the most important information. That is where Voyager 2 comes in. The instrument that was supposed to be dead here is something that the press releases tend to gloss over when they report on Voyager 2's crossing of the heliopause. The plasma science instrument on Voyager 2, the instrument that made its crossing historically unique, was not supposed to be working. Let me be more precise about that. It had not been the primary focus of mission operations for years. The instrument was aging, running on power that was being carefully rationed across a spacecraft that loses roughly 4 watts of electrical power every year as its nuclear batteries decay. Every year, mission controllers have to make decisions about which instruments to keep running and which to shut down, because there simply is not enough power for everything. By the time Voyager 2 was approaching the heliopause, the mission team was managing power across the spacecraft with the kind of precision that makes accountants look reckless. Every single watt mattered. Heaters for instruments had been turned off. Systems that had been running continuously since 1977 were being switched off one by one, like a traveler discarding supplies to survive a longer journey than originally planned. And yet, the plasma science instrument was still running. Degraded. Operating in conditions it was never designed to endure for 4 decades. But running. The backstory of keeping it alive is one of the great unsung engineering achievements of the entire space age. The team responsible for Voyager 2 at NASA's Jet Propulsion Laboratory developed what they described as careful power management strategies, adjusting heating cycles, modifying operating schedules, finding ways to keep a 40-year-old instrument functional across a distance that light itself takes more than 16 hours to cross. Think about what that means in practical terms. When engineers on Earth send a command to Voyager 2, they wait 16 hours and 45 minutes for the signal to arrive. Then they wait another 16 hours and 45 minutes for confirmation that the command was received and executed. Every decision takes over 33 hours to verify. Every adjustment to the spacecraft is an act of blind faith followed by a very long wait. These engineers were performing maintenance on a spacecraft they could not see, could not touch, and could not reach in any practical human lifetime, using hardware older than most of their junior colleagues, across a distance that makes the word remote completely inadequate. And they kept that plasma instrument alive long enough. When Voyager 2 crossed the heliopause on November 5, 2018, it was the only spacecraft in history to cross that boundary with a functioning plasma instrument. The only one in the entire history of space exploration. There will not be another one for decades, if ever, depending on how long the hardware survives. The data it captured in those crossing moments was, quite literally, irreplaceable. What Voyager 2 actually measured that no probe has ever measured before. So what did the plasma science instrument actually find? Because this is the part that caused the stunned silence in the room. This is the part that made scientists who had spent 30 years building models suddenly go very quiet and start revising their assumptions. The first thing Voyager 2 measured directly was the plasma density on either side of the heliopause. On the inside, solar wind plasma. On the outside, interstellar plasma. The instrument could detect both, measure both, and compare both in real time as the probe crossed through the boundary. What it found was that the heliopause is sharp. Genuinely, surprisingly, almost shockingly sharp. The models had predicted a gradual transition zone, a messy, turbulent region where solar material and interstellar material mixed and churned over a significant distance. What Voyager 2 measured was a boundary so abrupt that the transition happened across a distance that was almost startlingly thin relative to the scale of everything around it. Scientists described it as being far sharper than expected. The plasma environment on one side was recognizably different from the plasma environment on the other side, and the change between them happened fast. Not instantly, but far more like a wall than a gradual slope. This was new information. Voyager 1 could not have told us this because Voyager 1 could not measure plasma. Everything we thought we knew about the transition zone was inference, and some of that inference turned out to be wrong. The second major finding was about temperature and pressure. Voyager 2 measured the temperature of the plasma inside the heliosphere as the probe approached the boundary. Then it crossed. Then it measured the temperature of the interstellar plasma on the other side. The interstellar plasma was much hotter than the models predicted. This sounds strange because interstellar space is cold, and it is cold in the sense that it is nearly empty and the average temperature of the universe in that region is extremely low. But the sparse plasma that exists in interstellar space near the heliopause was warmer than the theoretical models expected. This discrepancy between predicted plasma temperature and measured plasma temperature is not a minor footnote. It is a significant puzzle. And we only know it exists because Voyager 2 had a working plasma instrument. The third finding was about the pressure balance at the boundary. The heliopause exists because the outward pressure of the solar wind balances the inward pressure of the interstellar medium. It is a standoff, a constant negotiation between two forces meeting at a point in space. Voyager 2's measurements showed that this pressure balance was more complex than expected, influenced by factors the models had underweighted. including magnetic pressure from the interstellar magnetic field and the contribution of energetic particles to the total pressure on both sides. Every one of these findings was only possible because of the plasma instrument. Every one of them refined, corrected, or complicated models that had been built on decades of indirect evidence. The thing nobody expected to find. Here is where it gets genuinely strange. And I say that as someone who has spent considerable time staring at astrophysics research papers at unreasonable hours of the night, which is a hobby I would not recommend to anyone who values their sleep or their social life. As Voyager 2 crossed the heliopause, the instruments detected something that the scientific team did not immediately know how to explain. Energetic particles, specifically cosmic rays from outside the solar system, were leaking inward through the boundary before the probe actually crossed it, and solar particles were leaking outward. The heliopause is not perfectly sealed. It is more like a membrane than a wall. Material seeps through it in both directions. Scientists knew this was theoretically possible. What they did not know was the scale and the mechanism. Voyager 2's data showed that the leakage was more significant than models had predicted. Galactic cosmic rays were penetrating the heliosphere's boundary and reaching Voyager 2's instruments before the crossing. Solar energetic particles were escaping into interstellar space after the crossing. This has direct implications for one of the most important functions the heliosphere serves, which is protecting the inner solar system from galactic cosmic rays. These are not gentle particles. Galactic cosmic rays are high-energy particles accelerated by supernova explosions and other violent events across the galaxy. They are the kind of radiation that poses a genuine hazard to human spaceflight beyond the protection of Earth's magnetic field. The heliosphere acts as a partial shield. Not a perfect shield, as Voyager 2's data demonstrated, but a significant one. The data showed that the boundary's shielding effectiveness varies, that there are mechanisms of leakage that are more complex than the simple model suggested, and that understanding those mechanisms matters enormously for planning future human exploration of deep space. But there was something else in the data that stopped researchers cold. In the region just beyond the heliopause, there appeared to be a thin layer of heated material, hotter than either the solar wind inside the boundary or the interstellar medium further out. A layer that seemed to represent solar material that had escaped the heliosphere and was accumulating just outside it. This feature had been theoretically predicted by some models and dismissed by others. Voyager 2 found it. A thin shell of material sitting just beyond the edge of our solar system, like a faint echo of everything the sun has ever exhaled, pooled at the boundary between home and the infinite dark. Nobody was expecting that data to be as clear as it was. Nobody was expecting the feature to be as distinct as Voyager 2's instruments revealed it to be. And nobody would have found it without that plasma instrument. Why this changes everything we thought we knew. Let us talk about what this all means, because the individual findings are remarkable, but the cumulative implication is the kind of thing that rewrites textbooks. Literally. Heliospheric physics textbooks published before 2018 describe a model of the heliopause that Voyager 2's data has now meaningfully revised. The first implication is about the shape of the heliosphere itself. For decades, the dominant model depicted the heliosphere as a comet-shaped structure, blunt at the front, facing the direction of the sun's travel through the galaxy, and trailing off into a long tail at the back. This model was built on theoretical arguments about how the solar wind should interact with the interstellar medium. But here is the thing. Voyager 1 crossed the heliopause at one point in space. Voyager 2 crossed it at a completely different point, because the two probes are traveling in different directions. Voyager 1 went north. Voyager 2 went south, and at a different angle. And the distances at which they crossed the boundary were surprisingly similar. If the heliosphere were strongly comet-shaped, with a compressed front and an extended tail, you would expect the boundary distances in different directions to vary significantly. The fact that both probes crossed at comparable distances in different directions suggests the heliosphere may be more spherical, or more symmetrical, than the dominant comet model predicted. This is not a settled question. Scientists are still debating it. But Voyager 2's crossing, combined with Voyager 1's crossing, gives us two data points that the models have to account for. And those two data points are already straining some of the assumptions that shaped heliospheric physics for 30 years. The second implication is for future human deep space travel. Any crewed mission beyond the solar system, which remains science fiction for now but will not remain science fiction forever, has to contend with galactic cosmic ray exposure. The heliosphere provides protection. Understanding exactly how that protection works, where it is stronger and where it leaks, what the boundary structure actually looks like from the inside and the outside, is not an academic question. It is an engineering requirement for keeping future astronauts alive. Voyager 2's plasma data provides constraints on those models that simply did not exist before. The models that mission planners use to calculate radiation exposure for future deep space missions are more accurate now than they were in 2017. That is a direct consequence of a 41-year-old spacecraft keeping one aging instrument alive long enough to cross a boundary at exactly the right moment. The third implication is perhaps the most profound, and the most unsettling if you think about it long enough. We have now had two probes cross the heliopause. We have two data points in two different directions. And both crossings surprised us. Both revealed things the models did not predict. Both raised new questions faster than they answered old ones. The universe is under no obligation to match our theories. The data from Voyager 2 made that plain. The engineers who performed surgery on a spacecraft 11 billion miles away. I want to pause here and talk about the human beings behind this, because the science is extraordinary, but the people are what make it something more than extraordinary. The Voyager mission at NASA's Jet Propulsion Laboratory has been running continuously since 1977. The team that manages it today is not the team that launched it. Most of the original engineers have retired or died. The knowledge of how these spacecraft work has been transferred across generations of mission controllers, documented in manuals and passed down in conversations, and inherited in the accumulated institutional memory of a team that refuses to let go. There are engineers on the current Voyager team who were not alive when the spacecraft launched. They are operating hardware that predates them, communicating in a programming language that almost nobody else in the world uses anymore, managing systems whose original documentation occasionally contains gaps that have to be bridged by very careful inference. When the decision was made to keep the plasma science instrument running on Voyager 2 as the probe approached the heliopause, it was not a simple call. Power was genuinely scarce. Every instrument kept running was an instrument drawing from a finite and shrinking supply. Keeping the plasma instrument alive potentially meant other instruments ran warmer or colder, or faced other stresses. The team made the call. They believed the science justified the risk. And then they managed the power across 33-hour communication round trips, adjusting and monitoring and correcting, for years, as the probe crept toward the boundary. When Voyager 2 finally crossed and the plasma data came in, the team had been preparing for that moment for years. Some of them had been preparing for it for most of their professional careers. Ed Stone, who served as the Voyager project scientist for decades, described the crossing as the beginning of a new era of exploration. He was not being dramatic. He was being precise. The data from Voyager 2's crossing opened questions that will occupy heliospheric scientists for the next generation. And the spacecraft responsible for all of it is a machine the size of a small car. Built with 1970s technology, running on roughly enough power to keep a few light bulbs on. Transmitting data at a rate that would make a 1990s dial-up modem feel superior, across a distance so vast that its signals take the better part of a day to reach us. And it is still going. What comes next, and what Voyager 2 is heading toward. As of right now, Voyager 2 is more than 12 billion miles from the Sun. It is traveling in the direction of the constellation Telescopium, which is visible from the southern hemisphere, which feels appropriate for a probe that spent part of its mission visiting the southern outer planets. It will never reach another star system in any human timescale. The nearest star system, Alpha Centauri, is about 4 light-years away. At Voyager 2's current speed, it would take approximately 40,000 years to cover that distance, by which point the probe will have been dead for 39,900 and some years, so we will not be getting any data from that particular journey. The spacecraft's power supply, a radioisotope thermoelectric generator running on plutonium-238, loses roughly 4 watts of output per year. Mission controllers have been turning off instruments and heaters to compensate, but there is a floor below which the spacecraft simply cannot function. Scientists estimate that Voyager 2 will run out of power to operate any scientific instruments sometime around 2025 or 2026, depending on how aggressively the team manages the power budget. After that, the probe will continue traveling. It will travel through interstellar space for millions of years after every instrument is dead, and every human civilization that built it has long since transformed into something unrecognizable. It carries a golden record containing sounds and images of Earth, in the deeply optimistic event that someone finds it someday. But before the lights go out, scientists are hoping Voyager 2 will continue transmitting whatever the remaining instruments can measure. Every additional data point from interstellar space is a data point that cannot be obtained any other way. The next probe deliberately designed to study the heliopause and interstellar space. The proposed interstellar probe mission exists currently as a concept study. Even if it were approved and funded tomorrow, it would not reach the heliopause for roughly 15 years after launch, and it would not be launched tomorrow. The Voyager probes remain the only direct source of in situ interstellar data for the foreseeable future. What Voyager 2 is heading toward, in the purely physical sense, is nothing in particular. Interstellar space, by definition, is mostly nothing. Thin plasma, the occasional dust grain, galactic cosmic rays, the faint background glow of the universe. It is not heading toward anything. It is heading through everything. Here's the thing about Voyager 2's achievement that I keep coming back to, and that I think gets lost in the technical language of plasma measurements and boundary layer dynamics and heliospheric models. In 1977, a group of human beings pointed 2 machines at the outer solar system and let them go. They knew they would never get them back. They knew the hardware would eventually fail. They knew the signals would grow fainter and fainter as the probes moved further away until one day there would be no signal at all. They did it anyway. And then another group of human beings, 41 years later, received data from one of those machines as it crossed the edge of the solar system, and found things they did not expect. Found that reality was more complex and more interesting than their best models had predicted. Found a sharp boundary where they expected gradual transition. Found a hotter interstellar plasma than the equations had suggested. Found a thin shell of leaked solar material pooling just outside the edge of home. Found that they were wrong, in the way that scientists most love to be wrong, because being wrong means there is more to learn. The reason Voyager 2's crossing matters more than Voyager 1's, in strict scientific terms, is the plasma instrument. The reason the plasma instrument was still working is the engineers who spent decades refusing to let it die. The reason those engineers kept fighting for it is that someone, somewhere in the chain of decisions that runs from 1977 to 2018, kept insisting that the data would be worth it. They were right. The data was worth it. Jeremy Wade, the man who spent 9 seasons hunting river monsters before finally admitting that the real story was what was happening to the rivers, eventually described himself as a witness, someone who happened to be in the right places at the right time. The scientists who built Voyager 2 were something different. They did not just witness, they reached. They built a machine and threw it past every planet in the outer solar system, and then kept talking to it for 4 decades until it crossed the edge of everything familiar and told them something true about the shape of the universe. That is not witnessing. That is the most stubbornly, magnificently human thing I can think of. We live inside the sun. We did not know that 200 years ago. We barely understood it 50 years ago. We understand it more today than we did in 2017 because of a piece of hardware the size of a small car, launched before home computers existed, powered by something roughly equivalent to a few refrigerator light bulbs, transmitting data home at speeds that would embarrass a fax machine across a distance that takes light itself 16 hours to cover. Voyager 1 got there first. Voyager 1 will always get credit for that, and it deserves it. But Voyager 2 got there with its eyes open. And what it saw changed what we know about the edge of home. That is what impossible looks like when human beings refuse to accept it.